This video is part of the MCAT chemistry video course. This video will cover nuclear decay, so first all the types of nuclear decay, and then we will go over half-lives. Before we look at the different types of decay, make sure you're good on this type of notation, where we have X, which just represents whatever element we're working with, and then notice how in a lot of these types of decay, your atomic number is going to change, which means that the number of protons changes, which means that the element identity will change. So anytime you see it go from X to Y, all that means is that the element identity changed because the atomic number changed. Our first type of nuclear decay is alpha decay. And in alpha decay, the nucleus loses 2 protons and 2 neutrons. And so these 2 protons and 2 neutrons are ejected from the nucleus of our original element, and they leave, and they're in the form of a helium nucleus because a helium nucleus has 2 protons. And so whenever it loses this molecule that has 2 protons and 2 neutrons, that is virtually a helium nucleus. And sometimes you will see it written as an alpha particle, and that alpha particle is the exact same thing. It still has the 2 protons and the 2 neutrons. And what happens to our original element is that the atomic number goes down by 2, and the atomic mass goes down by 4, because remember, atomic number is protons, and atomic mass is protons and neutrons. The next type of decay is beta decay, and beta decay is when a neutron basically turns into a proton. So you can kind of think of a neutron as the combination of a proton and an electron. So then when the neutron turns into a proton, it ejects that electron. And that's what we have on the right side here, is the electron that gets ejected from that nucleus. And that electron can also be written as a beta particle, which will be the letter B for beta, and then it will also have the negative charge. But either way, you can pretty much just think of it as an electron. And if we look at our original element, the atomic number goes up by 1 because 1 neutron turned into a proton, and then the mass stays the same because we lost a neutron, but then we gained a proton, and that the proton that the neutron turns into remains in the nucleus. So that proton does not get ejected. The next type of decay is beta positive decay. And in beta positive decay, we have a proton that turns into a neutron. And how you want to think of this is that a proton basically just loses its positive charge. And the way it does that is by ejecting this particle that's called a positron, which you can basically just think about as a positively charged electron. So when the proton loses that positive charge, it turns into a neutron. So our atomic number goes down by 1. We gained a neutron while we lost a proton. So they offset each other, so the atomic mass stays the same. For electron capture, you have an electron that gets too close to the nucleus, and then it combines with a proton, and that forms a neutron. So your atomic number goes down by 1 because 1 proton turned into a neutron, and the number of neutrons went up by 1 while the number of protons went down by 1, so your atomic mass stays the same because those two offset each other. And then just notice that we have an electron on the reactant side of this equation to show that the electron combined with the nucleus of that element X. And our last type of radioactive decay is gamma decay. And in gamma decay, the nucleus, all it does is goes from less stable to more stable. And anytime you go from less stable to more stable, you're going to release energy. And the nucleus releases this energy in the form of this symbol here, which is a gamma photon. So that is not a Y, that is gamma. And a gamma photon is just a super, super high energy form of light. If you look up a table of the electromagnetic spectrum, you'll see that the highest energy light will be gamma rays. So anytime you hear gamma rays or gamma photons, that's just talking about super, super high energy form of electromagnetic energy. And in gamma decay, our number of protons does not change and the number of neutrons does not change. So the atomic number and the atomic mass stay the exact same because the number of protons or neutrons have not changed. The last thing we'll go over is half-lives. And a half-life is how long it takes for half of a radioactive material to undergo its radioactive decay. And the amount of time that a half-life will be is extremely dependent on whatever element it is. So be prepared to see a very large variety of half-life lengths. And you want to think about this like every time a half-life passes, half of whatever sample you had will have undergone that decay. And a lot of times it's going to turn into a new element. Think about all the radioactive decay types we just looked at, how many of them turn one element into another. So a lot of times half of your substance turns into a new element, and then the other half of your substance is still that original element. And however much of your sample you're left with after one half-life, if another half-life passes, then you're going to be left with half of your remaining sample after that second half-life. So what you're basically doing is you're dividing your sample amount by 2 for every time a half-life passes. And then that will be how much of your original sample is remaining. And that gets summarized in this equation where we have N, the final amount, equals N0, which is your initial amount of your substance, times 1/2 raised to the power of the number of half-lives. And what this basically is you are taking 1/2, and however many half-lives you have, you're raising it to that power. And so what that means is you're dividing your initial amount by 2 for every half-life that you have. And let's just do one example with this equation. So in this problem, we will work with carbon, which has a half-life of 5,730 years. And we're starting with 500 grams of carbon, and we're asking how much of that original sample is left after 15,000 years. The first thing you want to do is figure out how many half-lives you have. And remember, for the MCAT, you can do some pretty generous rounding. So let's just do 15,000 divided by 5,730. And that's going to get us approximately 3. And again, that is pretty generous rounding, but you'll be fine doing that for this test. And then we're just going to plug all of our numbers into this equation, which is going to give us N for the final amount equals 500 times 1/2 raised to the third. And that equals 500 times 1/8, which is the same thing as 500 divided by 8. And that equals 62.5 grams remaining. And you can go about these problems just like what we just did, but you can also go about them by just dividing by 2 for every half-life that you calculated. So let's just look at how to solve it real quick if you want to take that route. So we start with 500 grams, and we're just going to divide this number by 2 for every half-life that we had. And I'm just going to draw an arrow to represent every half-life that passes. So after the first half-life, we have 250 grams. After the second half-life, we have 125 grams. And then after the third half-life, we will have 62.5 grams left. So you can take this route or the route before with the equation to solve your half-life problems, and that's going to get you through the majority of half-life problems on the MCAT.